Hi, this is a video to help you through equilibrium and weak acids and bases. Before we discuss weak acids and bases, we have to understand equilibrium. So we're going to set some ground rules. First, a chemical equilibrium is represented in a chemical equation using these double-headed arrows, or arrows that are pointing in both the forward and the reverse direction. Sometimes you'll see these arrows with a full head at either end or just a half of a head at either end. They mean the same thing, and they mean that the reaction is reversible. So it can go in the forward and the reverse direction. The second ground rule is that square brackets mean concentration. In the concentration unit, molarity. Let's look at a general equilibrium equation. Notice that I've used a double arrow to indicate that this is a chemical equilibrium. On this side of the equation, I have the reactants, and on this side, I have the products. The reactants A and B will react to form C and D, and vice versa. C and D can react to form A and B. The lowercase letters A, B, C, and D here represent coefficients. These are the numbers that you put in front of chemical formulas when you're balancing equations. They're coefficients. So they're whole numbers 1, 2, 3, 4, etc. On this chemical equation, I've put this K value over the arrow. K is the equilibrium constant. K represents the point at which the rates of reactions in the forward and the reverse directions are equal. That does not mean, however, that the amounts of reactants and products need to be equal at that point. K is defined as the products of the concentrations of each product raised to the power of its coefficient divided by the product of the concentrations of each reactant raised to the power of their coefficients. Notice how I've color-coded these things to show you where these numbers are coming from and where they end up in this formula. It's important to have a conceptual understanding of the meaning of this value. There are three zones that are important to know about. And those zones are when K is less than 1, equal to 1, or greater than 1. These zones can tell you something about the relative amounts of reactants and products at equilibrium. When K is less than 1, that must mean that the bottom here, or the denominator, must be a bigger number or a bigger value than the numerator or the top of this equation. When K is 1, that must mean there are more reactants at equilibrium than there are products. So anytime you have a K value that is less than 1, it tells you that the equilibrium lies to the left-hand side. When K is equal to 1, that must mean that the values on the numerator and the denominator are equal. And so there are equal amounts of reactants and products at equilibrium in the case that K is equal to 1. When K is greater than 1, that must mean that the numerator is a greater value than the denominator. And so the reaction lies to the right, or there are more products at equilibrium than there are reactants. Pause the video now and try to answer question number 1 on your activity. Here's the equilibrium expression in the general form, and here's the equilibrium expression for this particular reaction. Notice that heat is a product here. When heat is released, it is energy. It's energy being released in the form of heat. Because energy is released in this reaction, it's an exergonic reaction. Because that energy is released as heat, then it is exothermic. If heat was a reactant rather than a product, the reaction would be endothermic, and since heat is energy and the reaction would be absorbing energy, it would be endergonic. In this particular reaction, heat is released, and so this is an exothermic reaction. Notice that heat is not part of the equilibrium expression. Each K value depends on the temperature. If the temperature changes, the K value will change. But heat, as a reactant or a product, is not part of the equilibrium expression. The other thing that does not appear in the equilibrium expression is anything that is a pure liquid or a pure solid. If you see L or S as the phase of any of the reactants or products, you simply leave them out of the equilibrium expression. Now, if the K value for this reaction is 0.024 at room temperature, this number tells you, because it's less than 1, that there are more reactants, so there is more nitrogen and hydrogen gas, than there are products, ammonia, at equilibrium. Now let's talk about Le Chatelier's principle. Le Chatelier's principle says that at equilibrium, if something is changed, the reaction will shift to reach equilibrium again. When you change the concentrations of the things that are part of the equilibrium expression, you put the system out of equilibrium. And the system will try to reach equilibrium by converting reactants to products or products to reactants to reach equilibrium again. Remember, K is a constant value, and so K cannot change, but concentrations of these things can change to reach that K value. For example, if this is a reaction at equilibrium, and I add more nitrogen gas, or I add more hydrogen gas, that would mean that I would increase the concentration of the reactants in this reaction. I would put this equation out of equilibrium, and so it would have to shift to reach equilibrium again. It would shift in the forward direction. The excess reactants would react to form more products until the reaction reaches equilibrium. So if I add more reactants like nitrogen gas or hydrogen gas, the reaction will move forward to make more products until it reaches equilibrium. On the other hand, if I remove nitrogen gas or if I remove hydrogen gas, then there will be less reactants than there should be at equilibrium. And so some of the ammonia here will break apart or react to form more nitrogen gas and hydrogen gas to replace what was removed. In other words, if I remove any of the reactants, the equilibrium will shift to the left to replace them. A similar thing will happen if I change the concentration of ammonia. Heat acts just as if it were a normal product. If I add more ammonia gas to this equation, there will be more product than there should be, and so the equilibrium will shift in the reverse direction. So if I add more ammonia, I should get the shift this way. Likewise, if I add more heat, it will shift the equilibrium. Adding more heat will actually change the value of K because K depends on the temperature. But heat actually acts just as if it were a regular product. So you can treat it just as if you were adding more ammonia. When you add more heat, it shifts the equilibrium to the left. And likewise, if I remove ammonia or if I lower the temperature, removing the heat, it will shift the equilibrium to the right. Since pure liquids and pure solids do not appear in the equilibrium expression, they also do not affect the equilibrium when you change the amounts that are present. So any change in pure liquids or pure solids would not affect the equilibrium. Please pause the video now and try to answer the questions on this page of your activity. Let's make sure you have the equilibrium constant expression written correctly. Anytime you write an equilibrium expression, please make sure you write the K equal to the expression. In this case, I have the concentration of the product, I leave heat out of it, and then the concentrations of the two reactants where hydrogen gas is squared. This is the equilibrium expression for this chemical equation. If you're drawing an exergonic reaction, it's important that the energy level of the reactants is higher than the energy level of the products. The fact that the reaction is slow is really a relative term, but it means that this hill should be pretty high. Because the slow is a term that describes the rate, and it means that there's a high activation energy. If I draw the catalyzed version of this reaction, I shouldn't change the level of the reactants or the products. Those things remain the same. The catalyzed reaction simply has a lower activation energy barrier. The delta G is not changed overall. Something I didn't tell you is that the K value and the delta G are directly related. And so any change in delta G would change K. Since a catalyst does not change delta G or the free energy change, it also doesn't change the K value. So catalysts lower the activation energy, but they do not change the equilibrium constant. They don't affect the equilibrium at all. Another way to think about this is that the catalyst doesn't change the amount or the identity of the reactants or the products, and so it doesn't affect the equilibrium. It only changes the rate at which the equilibrium is reached. Now that we understand equilibrium a little bit better, let's talk about weak acids and weak bases. We saw these things earlier when we talked about weak electrolytes. We talked about carboxylic acids being weak acids and the fact that they partially dissociate, or only part of the carboxylic acid in solution will dissociate. Let's say about 10%. So maybe at equilibrium, you would have 90% of this and 10% of these things. And the same sort of thing happens for amines, which are weak bases. Only some of the amine in solution will react with water to form ions. These things are weak electrolytes because they form some ions in solution, but not very many. Here's an example of an acid-base reaction with the weak acid that's a carboxylic acid. This is the example that's on your activity. I'd like to point out that the thing here is labeled an acid. During this reaction, this structure loses a hydrogen. Remember the Bronsted-Lowry definition for an acid. An acid is something that loses a hydrogen ion during the reaction. In going from this carboxylic acid to this carboxylate, this molecule is acting as an acid. This is very typical behavior for carboxylic acid functional groups. During the reaction, water is turning into a hydronium ion, or H3O+, and water is gaining a hydrogen ion. Therefore, water here is acting as a base. Notice that I've also labeled acids and bases on the other side, or the product side of this reaction. And you can tell why if you look at the reaction in the reverse direction. This carboxylate, going in the backwards direction, turns into a carboxylic acid, and it gains a hydrogen. Therefore, going in the backwards direction, this is a base. On the other hand, this hydronium ion turns into water, or it loses a proton, and it is an acid. Conjugate acid-base pairs are two different structures that have almost identical formulas except that they differ by one proton. Here's an example. This acid-base pair is only different by one proton, the hydrogen ion. Notice that there's one extra hydrogen in this acidic structure than there is in the basic version of the conjugate pair. Notice that the charge on the atoms are not the same either. When you lose a proton and go into a carboxylate, you leave behind a negative charge. Here's the other conjugate acid-base pair here. Once again, the acidic version has one extra hydrogen ion compared to the base. And the acid should have a more positive charge than the base. In this case, it means that the acid has a positive charge and the base is neutral. In either case, the acid has one extra proton compared to the base, and the acid is more positive compared to the base. Please pause the video here and try the questions on this page of the activity. Let's try the example in number 3. This is asking you to label the conjugate acid and base pairs in the reaction. Let's look at what's happening here. Let's first label these things as acids and bases. Notice that ammonia is gaining a proton and going to NH4+. It's also getting more positive. If ammonia is gaining a proton, it must be the base. And the proton must be coming from the other reactant, water. So water must be losing a proton and water must be the acid in this reaction. Check to make sure that this is true. It is, because water becomes hydroxide ion with one less proton. So ammonia is the base and water is the acid. Going in the other direction, ammonium ion is losing a proton to become ammonia, and hydroxide ion is gaining a proton to become water. Therefore, ammonium ion is the acid and hydroxide ion is the base in the reverse direction. The conjugate acid-base pairs are the things that differ by only one proton. Ammonia and ammonium ion are similar except they differ by one proton. They are conjugate acid-base pairs. Water and hydroxide ion are similar except they differ by one proton, so they are also conjugate acid-base pairs. Once again, please note that the acid version has one more proton than the base in both cases. And the charges are different based on the number of protons present. Let's apply this to answer number 4. In 4a, it asks you to draw the conjugate base of H2S. If you're drawing the conjugate base of H2S, then H2S must be the acid version. The acid version has one extra proton. So when I draw the base, I must subtract one of the protons. If I remove a proton with a positive charge, I must leave a more negative charge behind. The conjugate base of H2S is HS-. The conjugate acid of hydroxide ion means that the hydroxide is the base. And so if I'm going to draw the acid, I have to add a proton. So I add a hydrogen with a positive charge. The positive charge of the extra proton is going to neutralize the negative charge. And my conjugate acid of hydroxide is water. If you haven't filled in the rest of these, pause the video now and complete the last two. Make sure that you understand before we move on. Okay, the conjugate acid of HPO4 2- must mean that we're adding a hydrogen because this is the base and I'm drawing the acid. So I'm going to add a hydrogen ion, which means that I'll add one extra hydrogen, and the positive charge from that proton is going to cancel out one of the minus charges here. So I go from a 2- to a 1- charge. The conjugate base of HCO3- has one less hydrogen ion and one more negative charge than its conjugate acid. Okay, now let's apply this to a chemical structure to draw the reaction products of an acid-base reaction. In number 5, this is telling you that lactic acid is acting as the acid. You should get used to noticing when you see a carboxylic acid and expect this functional group to act as an acid. The acidic proton is the hydrogen that's on the carboxylic acid. So this is the proton that will be removed, and it will be transferred to the other reactant, which must be acting as a base. So here, lactic acid is acting as the acid. It's going to donate this proton, and water will bond to that proton and act as the base. So in drawing the products of this reaction, all you have to do is draw the conjugate base of lactic acid and the conjugate acid of water. These are your products. And this is the conjugate base of lactic acid, and this is the conjugate acid of water. This is H3O+. You don't have to draw the structure. You could just write H3O+. Don't forget to complete this problem by following directions and labeling the conjugate acid-base pairs. Thanks for watching this video on chemical equilibrium and weak acids and bases. Please complete the check for understanding, check the key to make sure you're correct, and please let me know if this video is helpful.